So, today's lecture is going to cover topics from Chapter 1. As you guys are seniors in physics, I know that this is not your first science course, so I'm not going to bore you with going on and on about things like the scientific method, or things like what a hypothesis is, or any of that nonsense. I assume that you know that. I assume that you've seen it before. And so I'm not really going to concentrate on those sort of things. You should know what experiment is. You should know all those sorts of things. If you don't, or if you're confused, or if you've forgotten, feel free to pipe up with a question or whatnot. But we're not going to waste time on that, because you should have all seen that before. What we are going to talk about today is measurement, largely. We know that in physics and science in general, we tend to use the metric system, which means we're talking about meters, liters, kilograms, and seconds. And we hopefully know the abbreviations here: M, L, kg, and S. Right? Notice that the kilogram already has a prefix. Kilo meaning 1,000. So that's 1,000 grams. We can apply that prefix to any of these. We can have kiloseconds, kiloliters, kilometers, which is maybe the one we're most used to. So we know that these different units can have the different prefixes attached. So let's say we had 752 centimeters, and we wanted to convert that to some number of meters. Well, what's the proper way to do that? Well, we need to know how many centimeters are in a meter. So we're going to do some unit conversion. So here's how I do it. 752 centimeters, okay, over 1. It's always a good place to start. Now, centimeters. We want our answer not to be in centimeters. So we're going to put centimeters on the bottom of another fraction. We're going to multiply, so that when we multiply, it's going to cancel this centimeter with this centimeter, and it's going to go away. All right? Centimeters, and we want meters, so I'll put meters on top. Put meters on top, so we'll have some number of meters at the end. Now, we need to know how meters and centimeters are related, and hopefully that's one you know off the top of your head. And it says that 1 meter is 100 centimeters. So when we continue, when we just multiply across, 752 times 1 is 752. Centimeters cancel centimeters, so we're left with meters, and then 1 times 100 is 100. So we end up with 7.52 meters, and we've just converted. So that's not bad. Let's do one more real quick example. Let's say we wanted to go from 0.073 kilograms to grams, some number of grams. Well, 0.073 kilograms over 1 times, well, we want kilograms to go away, so we'll put kilograms on the bottom. We want to go to grams. Well, 1 kilogram is 1,000 grams. Multiply straight across, so our kilograms look like they're going to cancel out. So 1,000 times 0.073. So we're going to end up with what, 73 grams? Is that right? 1, 2, 3. Yeah. 73 grams, because on the bottom it's just 1. hopefully everyone can convert between metric units without much trouble. If I throw kind of one of the weirder prefixes at you, like pico or tera or some such, you might have to look it up, and that's okay. But they're all just factors of 100, so either 100,000, 10,000, 10 million, and so forth. So it get kind of ugly when we're trying to write it down, but it's not hard. But you can also do more complicated conversions, like going from meters per second to kilometers per hour. Well, let's talk about how we do it. Let's say we're going at 4 meters per second. And that sounds pretty slow until you think about 4 meters. That's over 10 feet. And then in 1 second, that's actually pretty quick. So I wonder how many kilometers per hour that is. Well, 4 meters per 1 second is really what this means. Meters per second. Alright? And we want to go to kilometers per hour. So let's handle kilometers first. We want kilometers. So that means we want to put meters on the bottom and kilometers on the top. We're doing that because we want the meters to cancel and we want to be left with kilometers. So we know that 1 kilometer is 1,000 meters. So if we multiply that across, we'll get kilometers per second. But that's not what we want. We want to get rid of seconds. So how can we get rid of seconds? I'll give you 2 options. So seconds on bottom, we're going to put 1 second on top. That way they'll cancel. There's actually not 1 second. I made a mistake. We'll put seconds on top. And what can we convert seconds to? Well, we may not know off the top of our head how many seconds are in an hour, but we should know that there are 60 seconds in 1 minute. So we'll do that for now. Alright? So that would cancel our seconds, but then we'd have kilometers per minute. And that's still not what we want. So we need to keep going. We need to cancel minutes. And we should know how many minutes are in an hour. It's 60. So now if we do this and we multiply straight across, we'll notice that we can cancel our meters, cancel our seconds, cancel our minutes, and we'll end up with 60 times 60 is 360, 3600. 3600 times 4, what is that? 1440. 14,400 kilometers per hour. Nope, wrong. I made a mistake that you'll probably make. So we get 1440 kilometers divided by 1,000 hours. So we have to divide this. This is going to give us 0 cancels, 0 cancels. 144 divided by 10, 14.4 kilometers per hour. So I'm glad I made that mistake because that's the sort of thing it's really easy to forget. You forget about a bottom, especially if it's just some factor of 10. You may see a bunch of zeros and think you can ignore it or something. So that's a very familiar conversion you'll have to do. You'll occasionally have to do it in reverse. You'll be given kilometers per hour and have to change to meters per second. One thing I do want to note is that instead of all this nonsense, hopefully many of you will get to the point where you'll just remember that there are 3,600 seconds in 1 hour. That's a useful fact to remember going forward. So that's a more complicated unit conversion, but it's still not that bad. You should be able to do this. It's basic arithmetic, really. This isn't even really algebra. I guess the canceling the units are, but this shouldn't be a problem. This type of process is also going to be useful to you as we move forward, not just for unit conversion, but for something that's called in science dimensional analysis. And dimensional analysis will help you not only make sure you got the right unit when you're doing some more complicated equations on in the future, it will also tell you whether you totally screwed up your problem. For instance, if you're trying to find distance, okay, distance should obviously be something like meters, centimeters, or some such. But if you found distance and you got grams per second squared, that's kind of screwed up. That's not going to work. So we'll talk more about that when we actually get to some more complicated equations and stuff. But you really need to be comfortable with this sort of thing, with this kind of process. It doesn't take long. You're going to get really good at it. You're going to get really fast at it. But it's something that we're going to have to do, and will really benefit you if you get good at it. All right. Along with measurement, we need to talk a little bit about precision and accuracy, and I'll very briefly talk about the difference, because it's one of those things that students often get backwards. If I could spell, we'd be in business. Precision versus accuracy. What is precision? What is accuracy? I'll start with accuracy because it's the more obvious one. Accuracy is how close to the actual value. Your book, I think, defines it differently, but I don't care, because that's really what it means. How close to the actual value a number is. If you are more accurate, you're closer to the actual value. If you are less accurate, you are farther away from the actual value. Precision means how, it's hard to put, sort of how reliable. So maybe like the reliability of your results, or of your measurements. So kind of consistency. A favorite example is kind of a picture of a dartboard. So we'll do a quick little sketch of it. So we got a dartboard and a dartboard. Okay. If all of the darts hit in there, then we are very accurate. If all of the darts hit here, then we are very precise. Okay. In fact, this is precise and accurate. This is just precise. Precise doesn't mean we're anywhere close to the real world. That just means that we get about the same result every time. So if we're weighing a 4-ounce weight, and we get 5.7, 5.72, 5.81, 5.76, then we are pretty precise. However, if we are getting 3.96, 4.04, 4.02, and so forth, then we are very accurate. We're nowhere close to the actual value here, but we're all kind of in the same ballpark, and we're very close to the actual value here. That's the difference between precision and accuracy. I have one more thing to say about that, and that is that precision, say we measure these same 4 ounces, say we maybe are a little more accurate this time, say we get 4.065. That is more precise than if we got 4.02. Why? Because it goes 1 degree farther, 1 decimal place further. So precision can depend on your measuring device. If our scale only goes to hundredths of an ounce, then we're going to be limited by that. But if our scale goes to thousandths of an ounce, then we'll have a more precise reading. It has nothing to do with how accurate our reading might be. It's just how precise, basically, our number could possibly be. Alright, the last topic I want to talk about today is everyone's favorite, significant figures. And sig figs are maybe the easiest hard thing in science. They are not hard, but every year I hear kids get so confused about it or claim that they have no idea how to do it or whatnot. So I'm going to do my best to give it to you as plainly as possible so that you'll know what you're doing. One thing I do need to mention is that in this class, we will only be worried about significant figures if we say that we're going to be worried about significant figures. With some of the problems and things that I do with Moodle, well, actually I'll show you. So here we go. These are the sorts of problems you'll see nearly every day. Probably not so much the multiple choice, though sometimes. And you see that these are just, basically physics problems. Do different things. Ball shot from a window 24 meters high. How long does it take to reach the ground? Some of you may know how to do that right now. Some may not. But on these questions, the numbers are randomly selected every time the question is generated. On most of them. On some they aren't for bizarre reasons. But, this 3.0, your neighbor might have gotten 4.6. This 1354, your neighbor might have gotten 1276. Who knows? Okay? So, the computer and Moodle, much like a calculator, can't do significant figures. So, you won't always be able to rely on them. So sometimes when we're specifically assessing whether you know what a significant figure is and how to use them, and we'll use them when we do like data gathering and stuff like that, we'll always use sig figs. So that'll be one thing. But when we're doing problems through Moodle, generally the rule is going to be rounded to 2 decimal places, and we'll talk about that as the year goes forward. But if we thought it was 4658, we can hit submit, and that's wrong. Hopefully, unless I'm just an amazingly good guesser. Yeah, it's wrong. And so we can keep trying until we get it right. And that's what I really like about Moodle, but that's neither here nor there. So that's that. But right now, I do need you to know about significant figures. So let's talk about where significant figures come from. So let's say that I have a line that's more or less straight, and I want to measure that line, and I want to measure it in centimeters. Well, let's see if I can trim that up some so that we can get a better reading on it. There we go. Okay, so let me grab this as close as I can. Here we go. And now we want to measure this. Well, really close. Okay, this looks like it's about 4 centimeters, but a little bit less than 4. So if we were estimating this, or rather if we were measuring this, we couldn't just say 4 because that wouldn't be precise. We'd have to say 3, but it's clearly like nearly 4, so we'd have to estimate. I would say probably 3.9 centimeters. The 3 is significant because we know that it's 3, like it's something over 3. This is a measured digit. The 9 is also significant because it's our estimated digit. Alright, so when we're actually gathering data, the digit that we actually measure, in this case 3, is significant, and then the digit that we have to estimate is also significant. Now this could be as little as 3.85 or as much as 3.95, or it could be anywhere in there. Alright, let's do it again, but this time let's use the millimeter side. Okay, and I'm going to draw another line. And let's measure this in centimeters. Oops. Oh, that's fine. Let's measure it in centimeters. So it's going to be 4 centimeters. And since we have millimeter marks, these are tenths of centimeters, so it looks like it's 5, 6, 7, not quite 8, so 4.7. These are both measured, so those are both significant. And then we have to estimate. See, it's almost 8 again, so I'm going to estimate about 4.78 centimeters. And again, all of these digits are significant. So we have 2 sig figs here, and we have 3 sig figs here. And that's really the most important thing I want you to know, is how to determine significant digits when you're gathering data. So when we drop the balls and figure out how long they take to hit the ground and how fast they're moving everything, I want you to know what the correct number of significant digits, significant figures to put would be. Okay, I'm going to take a few minutes and talk about, kind of review the basics of sig figs for you. If you know them, great, then don't bother listening to me. Or also, if you are very visual and you like charts and tables and stuff, the section on sig figs starts on about page 16 of the text, and there's a really good chart for how to determine if things are significant or how to do operations with sig figs and whatnot on page 18 and 19. There's your charts. But I'm going to talk through all the stuff anyway. But for those of you who'd rather just read it yourself and jog your own memory, here you go. So, first of all, numbers are significant. If I have 4.73, then that's 3 sig figs. If I have 87.248, that's 3 sig figs. Non-zero numbers are always significant. The problem arises when we have zeros, and it's not always clear what we're supposed to do. Zeros between non-zero numbers are always significant, so this would have 4. Similarly, if we had 86.003, since they're between non-zero numbers, this would have 5 significant figures. That's an easy enough rule. But leading zeros are not significant. So if we have 0.83, that's only 2 sig figs. If we have 0.000621, that's only 3 sig figs. Leading zeros are not significant, ever. Now the serious problem comes from trailing zeros. Trailing zeros may or may not be significant. They are always significant if they're after a decimal point. So this is 5 significant figures. 86.001000. That has 1, 2, 3, 4, 5, 6, 7, 8 significant figures, right? Yeah. 8 significant figures. So trailing zeros after a decimal point are always significant. However, trailing zeros like this, just 1,000, we don't know. Now, how am I telling you we don't know? Well, because we don't know. It may have 1, it may have 2, it may have 3, or it may have 4. It would depend on what instrument was used to measure this. If this 0 is an estimate, then it's 4 significant figures. If this 0 was an estimate, then it's 3, and so forth. Conventionally, we're going to say that these zeros are not significant. So generally when we see a number like that with trailing zeros without a decimal, we're going to say they're not significant. Okay. If they were significant, conventionally, if they were all significant, we would say 1.00 times 10 to the third. We'd write it in scientific notation. That way, this adheres to this rule. Alright, so if you have a number, not just in this class, but anywhere on tests or whatever in the future, and you need to convey that it has a certain number of significant figures or significant digits, and it has a bunch of trailing zeros that are significant, you need to do this. You probably need to put it in scientific notation. Alright, so that's how to identify the number of significant digits just for numbers. So the rule for addition and subtraction with significant figures is really simple, and it's place value based. So say we had 4.36 plus 0.124. Alright, well we can just add these normally, so it would be 4, 8, 4, 4, but this isn't what it should be. This is just the answer. We need to know how to round. Well, the rule for addition and subtraction is you look at the most precise place of the least precise number. That's really sloppy, but you get the idea. The most precise place of the least precise number. So here, 4.36 is the least precise number because it only goes 2/100ths. And the most precise place is 6, which is the 10th place. So that means we're going to round to the nearest 10th. So for this one, we would have 4.48. Okay, let's do a couple more. No. Alright, let's do subtraction. 14.624 minus 3.2. Okay, 4 minus 0 is 4, 2 minus 2 is 2, 6 minus 2 is 4, 14 minus 3 is 11. Okay, but we need the most precise place of the least precise number. The least precise number is 3.2 because it only goes to tenths, and the most precise place is tenths. So we're going to round to the nearest tenth. That's the rule for addition and subtraction. It's the most precise place of the least precise number. Another way to think about it is maybe is maybe to look at it this way. So we have a bunch of numbers: 14.263, 9.12, 123.49, and 3.0001. Okay. Underline the left, like the last digit of each. Yeah. Now the leftmost last digit is the digit that you round to. and I didn't do a real good job of staying in line here, but we can see that the hundredths place would be the leftmost last digit, or the leftmost last significant digit. So that's what we would round to. I don't know if that makes more sense or less. Let's do another one. 15.3, 210, 1242.6. Okay, here, let's underline the last significant digit of each. Okay, here, the tens place is the leftmost significant digit. So that's what we're going to round to when we add these up. So it's going to be 0.9745641. So we have to round this to the tens place, so it would be 1470. Alright, so if that makes more sense, use that. If the most precise digit of the least precise number makes sense, use that. It's really pretty simple, you just have to keep it straight in your head. For multiplication and division, it works like this. Let's say we had 4.63 times 0.12. Okay, you look at how many significant digits each has. This has 3 and this has 2. So when we multiply this, we're going to multiply and put our answer in the lowest number of significant digits. So I can't do that in my head. Hold on. 4.63 times 0.12. The true value is this, 0.55556. But we're going to round to 2 significant digits, and so we're going to just get 0.56. Right? You always round to the smallest number of significant digits. And that frustrates students sometimes if they've got something like 1576 times 2. Well, I probably could do that in my head, I'm just being lazy. Times 2, 3152. But pay attention to the fact that this has 4 sig figs and this only has 1, so we have to round this number to one significant figure. So this is just going to be 3000, and that upsets people sometimes, but that's the rule for significant figures. So for multiplication and division, you look at your number of significant digits, you find the one with the lowest number of significant digits, you multiply, and then you round to that number of significant digits. Now, the science rounding convention might be a little bit different from what you're accustomed to. Generally, basically it's the same as what you're used to. If we're rounding to the nearest tenth, then we've got 5.64, or 4.64 is going to round to 4.6. If we had 4.68, it would round to 4.7. Fine, whatever. That's easy. You know, anything less than 5 goes up, anything greater than 5, or excuse me, less than 5 goes down, or just gets truncated. Anything greater than 5 goes up. Awesome. The problem is, in science, if we have exactly 4.65 or 4.65 with a bunch of zeros, we are going to round that to 4.6. However, if there was anything non-zero over here, if we had 4.65163, we would round to 4.7. And that's the convention. And the explanation for this is on page 20, if you want to read it for yourself. But this is how we're going to do it. We're going to just be consistent. We're going to stick with your book on this. And when rounding, if it's exactly 0.5, if it's exactly 5, and then it's just zeros after, and we need to go to 2 sig figs, we're going to just truncate, or round down, sort of. And if it's above, anything above, even if it was 0001, we could round up. Make sure you ask me any questions that you have. If you're confused, look at the book a little bit more. Ask questions that could help from a neighbor, could help from me. Ask lots of questions as you're working on your classwork today. And that's all I have for today.